Okay, so we done with this classification. Now over here we discuss this slide discuss about class B amplifier. It says that the class B operation is illustrated in figure 7.6. So this is your 7.6 figure taken from Flight's book, where the output waveform is shown relative to the input in terms of time t. So you can see that in terms of the time instants, so for the time instant between this t1 and t0 and t1, the amplifier it operates, it conducts. Okay, so this is how, this is the amplification of the amplifier at the output. But if you see for the time duration between t1 and t2, there is no conduction. Okay, conduction is basically equal to 0. Okay, now its advantages is class B amplifier is more efficient. Okay, now remember, before we discuss this point, if I, for just for clarification, if I replace this amplifier by a class A amplifier, let's suppose any class A amplifier, so it means that for this input signal, okay, right, okay, what would happen that this class A amplifier would, okay, conducts, it would amplify for the entire cycle of the input signal, right? Okay, so basically this is your class A amplifier. And over here for class B amplifier, it conducts for one half cycle, either positive or negative half cycle of the input signal. So we have discussed the advantages, that what is the biggest advantages of class B amplifier, that it is more efficient. By more efficient means that if it is conducting for one half cycle, so the power dissipation, okay, in efficiency is a property of power dissipation, so the power dissipation can be decreased, and the amplifier can efficiently, okay, maximum power, we can say maximum power can be delivered to the load. The efficiency is good. Okay, so you can get over here, you can get more output power, okay, for a given amount of input power to the load, actually to the load. Okay, now the disadvantages is that it offers more distortion. By distortion we mean because of the absence of the negative half cycle. So there is no negative half cycle over here, there is no negative half cycle. So because of this fact, okay, the distortion is greater as compared to class A amplifier. Okay, in class A amplifier we have this positive and negative half cycle. But still in certain applications, okay, if your main concern is efficiency, if you want to have a more efficient mechanism operation, or you want to deliver more power to the load, so still your ultimate choice will be class B amplifier. Now next slide please. Okay, now this slide shows actually the working area, okay, or the region of operation region of the class B amplifier. Okay, so it says that the Q point is at the cutoff. It means that the operation point, okay, of this amplifier is of the class B amplifier is at the cutoff. Okay, so it means that the class B amplifier is biased, okay, at the cutoff point, so that ICQ is 0 and VCEQ is at the cutoff. Okay, it is brought out of the cutoff and operates in its linear region when the input signal drives the transistor into conduction, right? Okay, so this says that this is illustrated in figure this is figure 7.7 with the emitter follower circuit. Okay, this is a common collector amplifier where the output is not replica of the input. So this is more details, but the point, okay, the main point to understand is that this is a typical class B amplifier. Now if you see, there is no DC biasing at the base. At the base there is no resistor R1, okay, there is no resistor R2, okay, at the base at this point. Okay, so if there is no biasing at the base, okay, it means that if I draw the Q point, okay, so there is no biasing. It means that the base this base emitter junction is not in conduction, so the Q point or the amplifier is basically at the Q point, is at at the cutoff. This is your cutoff actually, this is your saturation. So the amplifier is always, class B amplifier is always at the cutoff. Why? Because of the fact there is no biasing at the base. Okay, so there is no conduction, okay, at the base. Okay, now if you compare this operation, now I'm talking about only this part, remember, okay, this part, okay, I'm talking about this part. I'm not including or adding this input signal. Okay, so for that I'm drawing this Q point, because this Q point, okay, if I this Q point, the biasing point depends upon the base biasing, okay, this one. So we can see there is no R1 and R2 over here in class B amplifier. So that's why we say that actually there, okay, the amplifier is in the cutoff region. This Q point is somewhere over here. Okay, now if I compare this class B amplifier with class A amplifier, let's suppose if I it happens to be a class A amplifier, so there was, remember, there was resistor, biasing resistor, okay, at the base. There was R1, okay, and there was R2 present at the base. Okay, so because of that, okay, the Q point was somewhere over in the middle. Okay, somewhere in the middle. So it means that if for class A amplifier, okay, there is conduction, or there is operation, okay, because of, okay, even though there is no signal. Okay, I'm not discussing again this signal part. Okay, I'm discussing about the biasing at the base. Okay, and how the amplifier differs when it operates in class A and class B amplifier, in class A and class B mode actually. So in class A, okay, there were resistors. Okay, so that biasing resistor at the base, it was pushing the amplifier, or it was making the amplifier to be in the conduction mode, okay, though there was no signal applied. Okay, so the Q point was over here. Now add over here in this scenario, which is in for class B case, that there is no R1 and R2 present at the base. There R1 and R2 present at the base. It means that there is no pre-biasing. Okay, so what happens that this Q point is basically shifted towards the cutoff region. So the amplifier is the cutoff region. So amplifier is not, okay, over here, amplifier is not conducting, right? Okay, okay, so okay, is not conducting. So this is the major difference of the Q point between the 2 points. Okay, now if the amplifier, if you apply the signal, okay, if you apply the signal at in the class B amplifier case over here in this part, okay, so what would happen that, okay, if I apply the input signal, okay, over here, this input signal goes into, okay, the amplifier, okay, the Q point, amplifier was in the cutoff in the Q point, okay, in the Q point. So what happens that sorry, let me mute this the speaker, so that we can, okay, so okay, so when, okay, so it means that now the input signal is going to forward bias this junction, okay, which is your VBE. Okay, so what happens that, okay, that if the input signal is applied at the base, okay, now the moment the input signal has a value greater than this junction voltage 0.7, okay, this base emitter junction would forward bias, and you would have what, a conduction, okay, at the output. So we say the amplifier, root amplifier, at the out, there is a signal at the output, this one, okay, and amplifier is conducting for the positive half cycle. Now when it comes into this part, the input signal comes into the negative part. Now remember, for the negative values, okay, the input signal cannot overcome the barrier voltage of positive of 0.7, so you cannot find any conduction over here, okay, so there is no conduction, okay. And then again, when it goes into the positive half cycle, whenever it finds, okay, a value greater than 0.7, so the amplifier conducts, and you can see this is for the other half cycle, for the positive half cycle. So interestingly, this operation is very similarly to your rectifier, okay. The only difference is the rectifier doesn't give you any amplification, and the power amplifier gives you amplification. Thank you.